Okay, hello everyone. Welcome in the second day of the Quantum Machine Learning workshop. And yeah, today we'll continue. And Jacob, if you are ready, I think we can start.
Okay, great. Welcome to day number 2. Today we're going to talk about quantum classification, also talk about integration of PennyLane with PyTorch, and then get into some advanced topics. But I thought that I had a lot of questions about how did we go about the exercise number 1. Remember how you fit the curve of this kind. So that's the second data set in the first session. And quite a few people ask that they had real difficulties to come up with a solution to this, because no matter what you do to the ansatz and the model, it will never fit it. And I said the problem is actually in data encoding. And the reason for that is actually explained in the presentation. The presentation said, if you encode the data from -6 to 6, then that data, it wraps around the Bloch sphere twice. And we have a number of different values which map into the same position on the Bloch sphere. And that causes ambiguity. The simple solution is to add this line. So those three are generating the data for this curve. And this one is scaling it back to the domain from -1.5 to +1.5, more or less. And that still creates ambiguity, but because of the symmetry of this curve, the same values map into the same amplitude. The same would happen with the sine function, which trains so well. So that was a simple solution. And if you train it, if you add re-uploading and all the wonderful things, then the curve will fit really, really nice. Okay, so that was the solution for yesterday. And today we're going to move into new things. So let's start with the classification. Let me just put the Zoom window up because people will be asking questions and I don't know where it is. Okay, it's more probably chat. Yep. Okay. Okay. All right. So let's get into it. And when we talk about any type of model, it's usually a good idea to start with how do we prepare the data. But first, let me clarify what is this classification about? What's a class? So basically, class is it's a sample of data. It's a group of data sample which is defined by unique nominal value, categorical value. It's one of the attributes. So for example, if we talk about cars, they could be grouped by color, such as red, yellow, green, which are classes for the color category, and size would be small, medium, and large. And your data could be classified by those labels. So the classification is the process of classifying data samples based on the attribute values, and for the future data to decide which class this particular observation, data, example belongs to. So if you see a car or some vehicle, we want to decide whether it's a sedan or a truck, especially if it's an unusual something in between, then you may have difficulties classifying that particular vehicle. So the classifier is a model predicting the class of a given sample, and ideally is to automating this process. And we have here a number of, let me just, I can't see what I'm doing here, a number of different classification models, quantum models, and the classical counterparts. So usually we have the whole richness of different modeling approaches. For quantum modeling, most of it is either theoretical or in research stages, whereas the classical models are working very well. So it's very difficult to create a good classification scheme using quantum computing techniques. Okay, so always good start is to to start with data preparation for it. And whatever we talked about before, all concerns about analysis and preparation of predictors is still applicable to classification. So that's not any different. But preparing the label is an issue. One of the problems is that quantum models are highly sensitive to the imbalance of classes. So if you have the category color, this could be a lot of, especially look at Teslas in Australia, every Tesla on the road is white. I don't know if that happens around the world, but white Teslas are terrible. They are everywhere. So every so often you find some other colors of Teslas. So they are the minority class, those other colors, whereas white color for Teslas is the majority class. So what happens is that if, let's say, only 2 or 3% of Teslas are not white, and we create a classifier that for every Tesla, no matter what color it is, we say it's white, we are 97% accurate. So we cannot actually trust accuracy score. And the worst could be if it happens to cancer patients that you say a so-called sink test. You take the test, you put it to the sink, and you say, no cancer, and the patient dies. So definitely the accuracy score is cannot be trusted when you have class imbalance. There's another statistic, it's called Cohen-Kappa statistic, which adjusts accuracy based on the distribution of the class value. And it doesn't give you very high accuracy scores. So if Cohen-Kappa is over 0.6, that's considered good. So if you take the measurement of the accuracy and kappa, and accuracy is high but kappa is low, then we have a problem. Please don't write on my screen. Someone wrote in green tick. Okay. So that's...
I will try to remove it. Oh, okay, it's removed.
Okay, so that's what we have other measurements of accuracy apart from simple accuracy score. And if you look at around PyTorch, for example, this PyTorch Ignite, it's got Cohen-Kappa function. So you could use it readily and start using it in your in classical or quantum modeling. So what happens when you have class imbalance? It's easy to spot it. You just look at the analysis of different class distribution. And a simple approach would be if you have a binary binomial classification, is either oversample the minority class or undersample majority class. So either start duplicating examples in the minority class or randomly removed examples from the majority class, hoping there is some redundancy in it. So the balancing usually leads to better results, and but it leads to incorrect accuracy because in the population you have a very different distribution than population in your model. And so the worst could happen is that often the data is given to you, a lot of free data around, it's already balanced so that you don't have any difficulties creating models. And if you don't know what was the distribution in the population, whatever result you're going to give is going to be wrong for the population. So definitely when you, actually the last slide in this pack, it shows you how to recalculate accuracy correctly for the population given the balanced data set. So definitely balancing is good because the classifiers don't have the bias, and some classifiers deal with class imbalance very well. A lot of decision tree approaches are constructed in a way that they look at the distribution of labels first and they adjust the decision making is to consider the imbalance of the class. There's also another interesting approach. It's called SMOTE, synthetic minority oversampling technique, and it's actually used very commonly. SMOTE creates synthetic, not real data points in the smaller label class. So what it does, it creates points in between points of a given class. So it uses some KNN approach, the nearest neighbor approach to create those artificial data points, and then looks at the distance to all the neighborhood data points, and based on the neighborhood, it classifies either one way or the other one. And if it's not in a minority class, it rejects it and starts again. So that's actually an interesting way, because your classifier is not then biased to specific data set. It's got some variety of different data. It's not specific replication of existing data. So there's also weighing data examples, which means if you do weight, which is inverse of the class frequency, and then you could, some models will take the weights into consideration when making decisions about classification. So SMOTE is also available for in the imbalance learn library, and it doesn't matter if it's a PyTorch or not. I think it's a general purpose, and it's all data preparation. It does not require a thesaurus. You just need to get your balancing of the class right. Okay, so we're coming into Penelane and PyTorch. So how difficult it is? I think that the difficulty is to understand how PyTorch is structuring a class, how it's structuring a model. So those of you who used some PyTorch before, you don't have any problems with that. Those of you who use some other packages like TensorFlow, it's all very similar. So in PyTorch, you create a class which describes your model. So on the left-hand side, it's a class of certain type. It's an NN module. It has a name, so it's a classing automobile. The initialization function, which will be executed when we create an instance of the class, a new specific object of that class. Then you have, within that initialization, you have a chance to create all the elements of the neural network, because this is a part of neural network. So PyTorch is excellent with neural networks, and neural networks we're going to use as a vehicle for the interface with Penelane. So in this particular case, in the initialization, we could create a number of layers. And I actually created here a separate function in which I create every single layer I need to use. I return every single layer as a list, and then wrap it around using the sequential structure, the sequential layering. If you want to use a functional approach, it's a bit more difficult with Penelane, so let's stick with this particular approach. For some reason, Penelane struggles when we have more complex forward steps. The forward step is when you apply the model to new data. So the new data is given, it's passed to the model, which was saved as a local instance variable, and the result is returned as the result of that function call. Now, when it comes to embedding Penelane models inside, it's almost the same. So we have a quantum automobile class. It's of the same type. We have initialization section. We're going to pass at the initialization additional information, like what type of simulator, Penelane simulator we're going to use, how many wires or qubits, how many layers, how many shots, and maybe additional information. The super call is to call the superclass to all the organization of that class. And we're going to save all the information that we passed in for later use into local instance variables. And again, we're going to create the layer. In this case, will be layer of one model, which is the layer consisting of the quantum model. And basically, we're going to save it for use with the forward, that means application to data. Now, what happens inside here is basically replication of what we did yesterday. So
Jacob,
we need to, yep.
sorry to interrupt you, but there was a question on the chat. Could you please use the pointer to show us what pieces of...
Yes, I'm using the pointer on a different screen now. I'm sorry.
Okay, thank you so much.
I need to face a different screen. Okay, since there is no camera switched on, I can do this. I apologize for this because I'm pointing all the time, and so yeah, that was a good.
Yeah,
thing.
we imagine we can see it now. Thank you.
Okay. Yeah. So here we have. I mentioned that it's initialization on the right-hand side. We request to create a list of layers in this neural network. It will be just one. And this is the definition of the layer. That layer is like any other quantum model. Okay, so we need to say what is the device type, and we refer to values which were passed in at the initialization and saved for later. We define the model, so we must have a model function outside. So this is the factory function, which generates a model. That model gets turned into the Q node, which is the quantum circuit. We specify that interface is PyTorch, so that first of all, the Pendelane knows to use PyTorch gradients. We specify what is device attached to the circuit, which model is derived from, and that's about it. That's an important part. The weight shapes. So when you look at the code later on, I'm going to point it out again, but basically the function that is generated at this step, the Q model PL, that function, the internal function, must have an argument called weight, the weights. So that argument needs to appear in this dictionary here. And it specifies basically what is the shape of the weight of the ansatz. So then we simply call torch layer, which is a special function which allows foreign layers to be inserted into the class. Someone likes to draw yellow on my screen. Yes, they did that too. Okay, so that actually created that layer, which then could be inserted into the whole sequence of layers. Some of them could be classical, some could be quantum, some could be of some other type. They could be matrices. So that's about it. We this way can define a quantum hybrid neural network in which some layers, in this particular case, just one layer we have here. This is the quantum layer, but on the left-hand side, you can see we have multiple classical layers, but one of them could be replaced by the quantum layer itself. So we're going to play with that in the next session. Okay. So at this point, we have to, did I get it right? Yep. Model training. Okay, so I pressed it twice. How do you train the model? We train it exactly the same way for PyTorch, classical models, as for hybrid models, and with Pendelane or not Pendelane. They are identical structures, no difference whatsoever. So before you train it, you how do I actually get the black thing off my screen? I don't know. Let me just check. Okay, so at the top you can see how we're going to call the. So this is actually testing part, I think. No, how do we call the class to create a quantum the quantum instance? And we provide all the information. So the shape one is the number of features or wires, number of layers, number of shots, and we can see them strange is a dot double. We turn it into basically appropriate floating point structure, so that we it's consistent with, especially if you start using GPUs, you have to make sure that all the tensors manipulated by by your program are of the same type, and they are on the same device. But we're not going to worry about GPUs with PyTorch in our sessions. Okay, so the top you can see how we're going to call it, but how we train this whole object. So it's the training is very similar to what we did with Pendelane itself. We initialize some. Need to start pointing in the correct screen. We initialize some collections that we want to accumulate. So like we want to have the history of accuracy, history of cost, history of parameters. They're basically lists of things on which every step of the optimizer run, we're going to save things for later use. When it comes to steps in here, they are very specific. So in the first step of each iteration, the optimizer is instructed to reinitialize its gradients. So every step, the gradients are being used to find the optimum at this step, the optimum for a given parameter values. So we need to initialize that. Then it's called step forward. So step forward is basically we call the model we apply to X parameters, and we get the result. This is actually calling the forward section in our model definition. Given the output, we could compare it to the truth to calculate the cost, and we could calculate some other indicators like accuracy. Then a step backward. The step backwards, basically, it's retraining all the parameters given the cost which was generated. So it basically does a small variations with the parameter values, and that actually completes that step. And then we ourselves, we start saving our cost, the accuracy, the parameters for later use. There's actually an interesting aspect here. If I want to use the parameters of this optimization and apply them, say, to test data, I actually need to know what is the model structure. We know it's a class. But the second thing is I need to be able to apply that model to the weights which were given at any given point in time in the optimization. So I need to save those weights. That's actually in PyTorch. This is done by calling the state dictionary. So every model has a state dictionary in which we have the parameter values at a given point in time in the optimization, but we have much more. So we have a lot of additional information. So you could actually look at that state dictionary to see what else the optimizer decides to keep in the model during optimization. So we may making a copy of it. I'm making a so-called deep copy because I don't want to simply save a reference to the model state because it will change in a minute. I'll make a copy of it and save it as optimal parameters at a given point in time. And I do it in a couple of places. I could save that on a disk if you want to. So whenever the state improves, I can save that. And the same exactly for the hybrid model. Okay, at some point, the model will be optimum. And the question now is, how do we find the optimal model? Depending on some circuit characteristics, some optimizer and training process hyperparameters. For example, the optimizer may have a learning rate. It may have some beta 1, beta 2. There's also parameters depending on which model you're using. The number of epochs, or even the whole different optimizers. So we have a lot of options in training. And so far we've been doing by trial and error, but there are better ways than that. So we tune the model by experimenting with all the combination of parameters. And we can actually do a systematic search for the best parameterization and hyperparameterization of the optimization process. So in scikit-learn and in PyTorch, we actually have support for the systematic approach called grid search. I've been trying to figure it out from Pendelane community and some of the unicorns in that community, whether those specific scikit-learn and so-called Scorch, there's a Scorch library for PyTorch, whether they would be applicable to Penny models, but people say they don't know. So it's I've never used it, but you can always do it by hand by creating the combination of parameter values. So we have two approaches to grid search. One is basically taking each different parameter which could control that model building, and basically take equal distance subdivisions of parameter values. So let's say we have parameter 1 and parameter 2 on the left-hand side, and the parameter 1 will be subdivided into equally distant value intervals, and the same with parameter 2. So in this case, we'll get 16 different parameter combinations, which could be used to create a model and train the model and get the outcome and apply it and see if the model is better or worse, especially on test data. There's another way of doing it. Instead of doing it in equidistance measurement intervals, we could make a random choice of different parameter combinations. And that actually reduces the number of combinations and gives you a better coverage of points on your cost landscape. As you can see here, because a lot of parameter values overlap on the cost landscape, a lot of those parameters will clash in when it comes to values. So that actually gives you a better coverage, but reduces the number of tests that you could perform. So that's a random grid search and a normal grid search, and it's worth pursuing it, especially if you deal with a lot of experiments to find out the best model. You don't need to have a Scorch, you don't need to have specific tools. You can organize it yourself and simply drive it through. And of course, rather than doing in Notebook, you would write a Python program so we could run in batch. So you could submit it in batch. It will go through the grid, create all possible tests, spend a week in testing the models and optimizing models, applying to test data, and then get the result at the end and finished. So definitely you need to be smart about that. Now here is the example of PennyLane with PyTorch. And you can see here on the right-hand side, we have a beautiful curves, smooth. Whenever we used the hybrid approach with PennyLane in it. On the left-hand side, we have rough and ugly, but viciously efficient PyTorch, pure PyTorch curves. You can see here that when it comes to some values, PyTorch is overtraining the data. So very quickly, on test data, the tests get much worse indicators, performance indicators, while the model is still improving. So on tests, mean square error, the best mean square error is at iteration 36, whereas here, iteration 79, and we obtain better test score for hybrid model, including PennyLane. The same with R squared. Now, that's actually misleading. It's misleading for one good reason is a lot of people who publish papers and say, I created this quantum model and it's better than a classical model. Okay, and here's the result, chart like this. The issue is that people don't spend any time tuning classical models. They take it out of the blocks, apply it, and you get this result, and you could claim, you have a claim to fame that you have a model, quantum model, which performs wonderfully. It doesn't. If you spend any time on your classical model in tuning, consider different options, regularization, and so on, this classical model is going to beat the hybrid model. This one. It's very easy. I can demonstrate it by simply removing layers of this quantum, of this classical model. It will improve. So sad case, a lot of people don't spend any time improving the classical model when they compare it against hybrid models. It's actually another thing. So we found the best model. It gives us the best accuracy. That's not the point to stop. At this point, what you can do is to start adjusting the classification threshold. So those people who are in machine learning, you know that the best accuracy is only the starting point, because normally the accuracy is calculated based on the threshold of 0.5. You look at confidence factors which are returned from your model. And if you adjust the threshold up or down, you could get better accuracy. This is shown here. We have here the misclassification examples and correctly classified examples. And when you change the threshold, you could actually at 0.3 threshold, you have accuracy 70%. At 0.75 threshold, the accuracy is 75%. So you can actually improve it. And you can actually look at so-called ROC curve, receiver operating characteristic curve, which was invented by British during the Second World War, when they wanted to differentiate between bombers approaching London versus birds flying. And the radar was used and it was misclassifying birds as bombers. So they invented ROC chart, which helps them understanding which classification method is better than others. So the area under the curve of all possible thresholds that you could consider for this particular model, the larger the AUC area, the better is the classifier. So you could actually use this technique to compare one classifier against the other. There's a whole field behind it. I just highlight there is such a thing. Problems and solutions, as always, there's lots of issues. First of all, if you make too simple approach to data encoding, it will give you some biases. You could lose information. You get ambiguities, difficulties training. So always look for a good quality approach to data encoding. You could even use trainable embeddings. You could have a quantum neural network itself as a model for embedding and encoding data. We have problems with imbalanced data. I showed you what you can do with this, oversampling, undersampling. And if you have barren plateaus developing, they could develop in all quantum models. Regularization in the classical post-processing could help. So not only you can play with the quantum model itself, but the classical counterpart, the other components in the hybrid model could avoid barren plateaus. We have overfitting problems, especially the classical part overfits very quickly. And one issue with that could be too many parameters. So the model learns by heart. You could reduce the number of parameters, and dimensionality reduction could help, like PCA. You could also use dropout layers and other regularization techniques, standard in classical machine learning. And that's about it. Always compare it against classical model. If you have a hybrid model, always try to remove your quantum model and see if you get an improvement in the classical model. So that's always a good test. You say by adding classical component to quantum component, we improved. Now you take the quantum component out. You may still improve because it's maybe spotting the results. So beware, always compare against other options. That takes us to the end. This is the data we're going to use. I'll talk about it in a short demo. And there's, of course, more. There's issues about, which I mentioned, if you have different distribution in the population than in the data, this is how you could recalculate your results once you work with balanced data to train the model. So that's the end of this presentation. Now the question is, let's look at the example, and I'll do it very quickly. It's always a problem Okay, so this is what you're going to work with, a simple quantum classifier. The first task here is look at the data you're working with. That's actually very important that you start when you split into partitions for training and testing and then validation possibly. You have to make sure that each partition has a distribution of classes which is in the population. So it's a similar distribution of classes. If your data hasn't been shuffled, it's in order of labels because someone decided to do it this way. And let's say you have a minority class at the end and you train on 70% of data, the classifier will never see the other label. So make sure you shuffle your data well. And this data has been shuffled, but not well enough. So that's one of the things to do is to shuffle it. So explore the data. Then we need to reduce dimensionality. I offered 3 options here. Your intuition, my intuition, which is completely wrong. Use statistical methods like chi-square or ANOVA F-test, or use PCA. There's lots of different approaches. One of them is better than others. And then improve the model performance. And the difficult part will be after doing all the preparation of data and how you apply to new data. Okay, that's the main difficulty of this little exercise, apart from working with the hybrid approaches. So very quickly running through. PennyLane, as always, and we included here PyTorch. I want to reduce my data from, I don't know, about 40 features to 5. We're going to see the data very soon. So I'm loading it from UCI. And this is the data of all different sample cars. They're different prices. They take, is a highway miles per gallon. So this is American data set, city miles per gallon, the horsepower, and so on. Of course, we have some data which is categorical. The engine location front and back, the body style, and lots of different, there's actually much more because we can see dots in between. We're going to make your life simpler. Here's something for you to play, see what the data looks like, especially the label, and whether you need to shuffle it. And there's different approaches to shuffling. I'll let you figure it out. We're going to start with simple things. Let's look at numerical data only. So we rejected all non-numerical columns. So here we work here with pandas data frames. So it's much easier to manipulate them. And those are they're just numerical features of this data. There's a lot of them. It will be difficult to use all of them to create a quantum model. Also, we have some missing values. So here's a look at which features have how many values missing, and we need to do something about it. Missing values, normalized losses, 4-to-1 records some missing values. That could be bad. So one thing is to replace missing values with some value. I'm going to use a very simple approach, and for each column, the missing value will be replaced with the mean of that column. And after that, we can see I don't have any missing values in any column. We standardize predictors at this point. I'm going to standardize it again, but if we decide, so now it's a standardized value 0 to 1, that's actually the plot of distributions. There's a lot of things that should be still done about that. But why I standardize at this moment in time? Because when I reduce data dimensionality with PCA ideally should receive data which is standardized. So I standardize early. Now prepare the label. The label is multinomial. This is the distribution of different classes in the label. And somewhere up there, it said that the negative values are safe and positive values are risky. So each car has a different level of a risk factor for insurance purposes. The mean is around 0.8, and I simply assume that all the things on the right-hand side will be 1, all the values on the left will be 0. So I'm going to use some kind of a simplified risk factors. One of the challenges will be to create a model for by multinomial classification, going back to the original representation of data. So this is safe is 0, risky is 1. So that's our data, much simpler to work with binary classification. Now, lots of different ways of reducing data dimensionality. Those are all the columns I need to worry about. Which of those features I should select? Well, my hunch said the risky cars are expensive. The gas guzzlers in the city on the highway with high RPMs with huge horsepower. Okay, I found out that's not the case. If we use statistical approach, the ANOVA F-test or chi-square, the chi-square approach usually is applicable more to categorical value, but chi-square is automatically binning data, so you could apply it to numerical values as well. So here is the code for that. It thinks that the most important against the label which we have is the weight, the height, the length, the wheelbase, and the number of doors. Looks like those guys with insurance purposes, they look at the car, say 2 doors, high risk, 6 doors, no risk, maybe. And this is the using standard PCA. So we rotate the axis of our data set in space in such a way that the highest variance of data is the first principal component, the second principal amount, and the 5 principal components explain 87% of variance in data. So we lost some information in the process. And here is where I could select which method I want to use. I started in your notebook, it says start with hunch, but you could guess that hunch is not the best approach. Let's start with the next one, which is using statistical method. So I'm using k-best. And like before, I specify mean square error, accuracy, and some other functions. I use it by hand, not to use during the optimization process the scikit-learn functions because they don't understand the gradients. I need to specify what are the devices on my computer. This is actually for the PennyLane only, and the rest is for PyTorch. I could never get to work a mix of GPU programs which are running PennyLane and PyTorch running on the same GPU. I'm using Lightning Qubit here. It's a bit faster than default Qubit, but you need to have it installed. The standard installation installs it for you. And let's run it. So number of wires, layers. Let me see what we get from this. I use 80 epochs. You could use less if that takes too long. More pre-processing, but now I'm going to pre-process to target my encoding technique. So scale it to the range of angles and split it into training and testing data sets, and then converting all of them into tensors of specific tensor floating point number double precision. Okay, the model, as explained in the last session, I'm using the function factory to generate models. And just next to it, I keep the function that knows what is the shape of that model, the weight of that model. We discussed it a moment ago, what it looks like and what are the components of the model. It's a hybrid model with one of the layers to be the actual quantum circuit. And this function, it's a utility function which I plugged in. You could always call it to see what is the circuit, what the circuit looks like. So I just saved my circuit into the local variable. So now I can actually look at its structure and draw its circuit. So this is the model which is sitting inside the hybrid PyTorch Pendelane model. And there's nothing else apart from this layer. So we'll see if it works. We have a training loop. It's just a function. And then the loop itself. Note the complexity here to ensure repeatability. It's not simply NumPy seed, random seed. We have one for torch, one for torch in case it's running on GPU, run on CUDA version of neural networks, and so on and so on. So if you want repeatability, you need to do that. We create the model, PyTorch model. We assign PyTorch mean square error loss. So I'm not going to use my own function. PyTorch comes with its own functions for that. We use PyTorch optimizer. There's a huge range of optimizers in PyTorch. Then we create the PyTorch model with Pendelane model inside, and we train it. So now we get the results. And we'll see if we get any better than before. Here's the reason why I'm doing accuracy calculation within the loop. Normally, we would simply keep the cost and then do scoring of the model later on. Okay, but if that is going to run for several days and I'm staring at the cost, I really don't understand what does it mean. Is the cost 0.14 good or bad? When I see accuracy, I can relate to it and I can see that the model is improving. Okay, so we have 80 epochs and a good accuracy of 86% or 87%. And then we could calculate other scores, especially for test data. So I'm having a taste, mean square error history, accuracy, and here I could use any other form of accuracy because I'm just applying it to plain values. So I could use scikit-learn measures of accuracy and mean square error. Now, I mentioned to you that I was saving the parameters by using the function within training, which is to get the state dictionary of the model. And I kept it and I was adding it, accumulating it in the history of parameters. And so here, I need to be able to get it back. And I'll go through the range of history of parameters. And for each step, I need to load it back. So I need to load the model with the parameter set and more from that history. So load state dictionary. So that's a PyTorch thing. Okay, so the model, we could save the state dictionary, the state of the model, and then load the state from elsewhere. It could be from disk. And here it is. It says accuracy is higher than in testing than in training. Anybody knows why? And a plot here, so you could appreciate. The accuracy in testing at 51 is better. So it's a dip somewhere here. It's better than training. That's unusual. It should not be happening because the data wasn't shuffled properly. True, exactly. So this is actually a good sign. It usually comes in small data sets. So in small data sets, you could get always unusual test data. And here it's not only small, but it's not shuffled properly. So whenever you see this, that the test score is better than training score, that's very suspicious. So something wrong with your partitioning of data. Okay, so what you have to do, you have more time now. You could start playing with this with the model and especially see if you could improve that. Can you improve it, first of all, by changing a different way of reducing the dimensionality? I picked the K-best, which means I kept the actual features. You would think that doing PCA would be a better approach because PCA is considering variance of principal components. Do I think PCA is good practice? It depends. If you work in the bank and the manager is going to come to you and say, which of our important variables, customer savings variables are most important? I would say, I don't know, I have PCA. Okay, so in this case, it's probably not. And you would stick to meaningful variables in your model. So, but when it comes to technical aspects, I would have several different ways and find which one gives me the better outcome. But PCA is a standard in scientific approaches, so it should give you a better approach, a better selection of variables, even though they're meaningless. You could actually cast it back into the original vectors, original tables, because the PCA is only variable names. Each row is actually taken from my data frame, so I know which was the actual original set of features attached to that particular row. Can we use nonlinear autoencoders for dimensionality reduction? Yeah, why not? So test it out, okay? It's more complicated, but we can. So now you operate in PyTorch environment, which is much richer than PennyLane. So that's actually a great way of doing your quantum modeling. We now are doing it in a very rich environment, and we have huge number of the PyTorch community is many times more, it's larger than PennyLane community. So now you embedded your PennyLane model in a large classical environment. So it's actually a great way of sorting it out. So is there anyone here who is happy to do your own things? Actually, where is my Zoom? I don't have, oh, my Zoom is here. I need to look at the participants. Okay. So if you feel you're good, go for it and start playing with this. So what I'll do now, and I have here half an hour to do this. I'm going to slowly walk you through some of the steps. I actually have here my cheat sheet because I have here the answers to my solutions. I hope that's the one. Yes, something, is it from the answers? Yes, okay. So I solved it all beforehand. And I'm going to post, I'm going to find out if I'm going to post the answers or not. But let's look at the data. So the first thing is I look at the class. So I look at the class. It's actually a column in the data frame. So I cast it to NumPy so it takes less space and reshape it so I can actually see it. If we look at it, you can see that we have negative values and positive values interspersed, but most of the low values are at the end. So that data has not been shuffled well. Okay, so that's the first observation. It is sort of random, but most of the high values are summed up to here. So if we have 70-30% split without shuffling, we're going to be in trouble. Unless we shuffle it at the time of splitting into training and test partitions. However, very improperly, I will be doing PCA beforehand. So normally the principal components should be done on training data only, and then the model could be applied to test data separately, but we do it together. So that's not how it would work in the reality. Variation quantum circuits for multi-class classification. I had a problem of trained model. Instead of finding 5 different classes, it acts the problem like a binary classification. Yeah, because we converted the 5-class variable to 2-class variable here. Okay, so we're not doing a multi-class classification at the moment. That's actually one of the challenges, to go back to multinomial case and try to do classification for the multinomial example. That's actually will be much more difficult task. Okay, so I'm here at this step. The question is, how do I shuffle it? I have my Y class and X class separately. There are 2 ways of doing it. Either put them together in a common data frame and then shuffle it and then put them separately, or you could do it the way I've done it here. It's a more difficult way, where you shuffle the index of one of the X variables, and then you reindex Y variables in the same way. Okay, so we do permutations on the X data frame index. So we're not shuffling the actual rows yet. We're just shuffling the order of the index. And then we are physically shuffling the rows according to the new index. And then we do exactly in the same order for the Y class, which is the label. Okay, so that's one way of doing the shuffling. So after shuffling, we have a better, it looks better. So negative values and high values are all over the place. If I were to do it from the top of my head, it would be simpler to put Y and X together into one data frame. It's a shuffle, a data frame, and then split it. Okay. But I try to do it differently to give you an idea that, yep, you could be shuffling indices rather than rows. So we're going to do numerical predictors only. So I'm going to run it from the beginning, because that's probably never run. Okay, so now we have a random distribution, better. We do the same way, so all the things the same way. We getting rid of missing values. We standardize the predictors. We could look at the plot. We're going to convert the multinomial case to the binomial case. That's why Batu had that question, I imagine, because it comes up as binomial, but it started as multinomial. It's a question about Cohen kappa. Sometimes it gives you values, infinite values, possibly because you have missing values. But I would have to look at a specific example. Reduced data dimensionality. So now it's basically from 17 to 5. I'm not going to bother doing hunch. It will not work. Trust me. It gives you very bad results. We tried K-best. I have it in the other worksheet. Let's try the PCA on shuffled data. So I'm going to use the XPCA columns here. Let's run it. What I did here, I increased the margin. I think the other margin was much smaller. if you can recall, we played with the range of values and increasing the margin. So here's a margin 0.1. I thought, okay, since it worked before, I'll try it. Increase the margin to 0.5. Oops, the wrong one. Let's do this. 80 epochs, everything else the same. Q model, key shape. And I'm going to run it and see if we get better results or not. That's 40. Okay, it reached some of these scores much earlier. 85, 56. But it's not going to get any better. Looks like it, maybe. So shuffling did not make much difference. Okay. So we got exactly the same result. So there must be something else better. So PCA versus others gives you exactly the same result for some reason. Which shouldn't. What did I apply here? XBest. So there must be better ways of doing it. So any suggestions? The charts look different. One thing is that my test scores are worse than training scores. So that's actually a good sign. And my accuracy for test data is worse. So at least I know that the data, there's nothing wrong with data partitions. Okay, so the data is true, it's usable. Okay, now if you can think of something, suggest something. What should I do? What suggestion did I make? I mean, one possibility is to put data re-uploading. That will definitely improve it for this data. Actually, there are tasks to do. Changes apply to data training, features. We could try to increase number of features from 5 to 6 or 7. At the moment, 87% of variance is catered for. So that's actually a possibility. So at the moment, the PCA is using 5 features. What would happen if we increase it to 6 or 7 features? Now that will increase the model size. I could have simply run all of it from scratch. We have much more variance retained in the data. So if we go up, we can probably see that the PCA now explains 92% of variance in data. So it will be a much stronger model. So we reduced 17 features to 7, and we are reaching over 90% of information contained in the original data set. So hopefully it should give us better result. So that's actually a nice thing about PCA, is that we have a smooth transition from the number of parameters. Whereas if you pick the next feature, you don't get such a smooth transition from between numbers of features. Okay, you can see accuracy is growing much slower, so it's quite possible that we need to increase number of epochs for that case. So we didn't get such good result as before, only 78%. But if you look at the shape, it's probably going to grow much slower. So never simply wait for good answers, be patient. When you get worse result, it doesn't mean it's going to get worse because it's growing maybe more consistently. Always look at the plot. The test data passed earlier. Okay. The question is it completely flat or is still pointing down? If it's still pointing down, maybe we need to increase the number of epochs. Okay, so we can play with that much more, but we are reaching the end of this session. Okay, so what I'm going to do during, I'm going to have 10 minutes break because I think that we are 6:30, 1.5 hours. Pavel, help me here.
Yes. Yeah, so the plan was to have the first part completed in 90 minutes. So I think we are even 20 minutes ahead. And then
Oh,
there was a plan. Yeah, so I think we are ahead of the schedule now.
Okay, 6:30. Okay. Oh, so I can still spend some time. Okay. But we're going to have a break for half an hour, right?
Yes, yes. At 12. So according to the agenda, it should start in about 20 minutes.
All right. So the question is now how you apply that model, because we can actually improve it. I can see that that curve, the test curve is still pointing down. So if we extend it, I'm sure I could get at least the same level of accuracy as with the previous model. I could also play with the size and the structure of my ansatz of the quantum model. Definitely, if I put re-uploading model in, it will be much better. That's what I did with yesterday's estimating model. I plugged in the re-uploading model. I got much better results. Okay, and it's not difficult. In fact, I was advising someone that do not use angle encoding layer because you're going to get errors. No, it's not problems. You can do it. You just have to make sure that you don't actually encode more data than the number of qubits you have to your disposal. So you have to encode equal number of input data or less than number of qubits. Otherwise, that's the only thing you have to do. So it's not difficult to construct that model. I can show it to you in a second, but let's focus on the next step, which is how you apply this model to new data. What we have to do is to look back at the data is going to come in the original form. We selected some numerical variables and we selected a number of features, or in this case, we reduce those features to using PCA. So what we have to do when we create new cars, we could actually split some cars off. And you have to process the data exactly the same way as you were processing data for training. So what type of transformations we've done? So first of all, I selected, where is it? Accuracy. Okay. So we selected only numerical predictor. So if I create new rows, so new cars are arriving, and I want to apply my model to decide whether it's a risky car or not. So what we have to do, first of all, we have to get rid of empty fields. So identify, have we got empty columns or not? When you get new cars, we could say the new rules apply. Whoever enters the data entry, people cannot skip fields. Okay, so we can actually use it, or we could start filling it in with the means which we derive from training data. So get rid of missing values. Then we need to standardize the predictors the same way. So we have to apply not the, we can't actually start creating a new scalar. We have to use this particular scalar, which was used in training, and this scalar should be applied to the new data. Okay, keep it in mind. So we need to scale it using this scalar, autoscalar, which was fitted on training data. Okay, so scaled is called scale, the scalar. We were playing with the label distribution, and we don't have the label here because we want the label to be predicted. Binary label, unfortunately. We will not be able to cast it back into 5 class label. Then we decided to use PCA. So PCA created a model which was trained on training data. Actually, there was all data, but normally on training data. And the PCA model, that particular model, we have to apply to the new data so that the new data is going to map into the same coordinate system as the data which was transformed with PCA. And then we have to apply another scalar, which was to scale it now into the data encoding values. So this scalar will have to be applied as well. Okay, and then we could apply the model which we just created. We could save that model on disk. And this is how we do it. So here I have an example. I have created actually some 3 cars. So I used only numerical value, and I plugged in some numerical values for 3 cars using price, hour, MPG. So all the 17 values are plugged in from the top of my head. And I read this string back to get the data frame. Okay, so that's a simple way of getting data, not from disk, but from middle of your code. I'm using string IO library, or the IO library. And then I'm applying. So I make, I do the transformations. I create a data frame. I do the first scalar, and I borrow columns from this original. So this particular data frame, it's got all the column names here. So basically, I'm saying create the new transformation, apply the previous scalar to this data, and retain the columns. And this is the first standardization. Then I'm doing the PCA transformation, the alt transformation, the same as I used before, but I transform just the 3 records. So this is the PCA version of it. And I get the columns. So basically, the names, I want to retain the names as before. So I have 3 names. And then I do the second scaling to map the data into the angles. And then I make it a tensor. So to be able to apply the model, this data has to be in TensorFlow. And the model was applied here somewhere. Where is it? Array, 3 Oh, here it is. And then I use the model applied to the tensor. And the results, I simply compared with 0.5. That's my threshold. And I have the results for those 3 data. So the first car is not risky, and the next 2 cars are risky. And that's because they have very few doors. The fewer the doors, the riskier the car, according to the US insurance inspectors. Can we try using sigmoid? Yes, they're going ahead because the next session is going to be that. So basically, in the next session, we're going to use exactly the same data, but the question is basically what we're trying to do here. We're trying to get binomial outcome using a linear separation of data that's not appropriate. So we really need to fit it into binomial outcome, and sigmoid is exactly what we need to do. So Afan is actually giving us a good suggestion, and you are going to see something amazing when we do that, because then what's going to happen is that our quantum model is linear. It returns linear outcome. It doesn't matter if it collapses into binary outcome, but it's a linear model. But the classical model is going to help us because it will convert the frequency distribution into a squashed sigmoid function, which will much better meet the training results. And the result of that, of doing this, will be a huge performance boost in training. And that's something that it's not anticipated, because if we train the quantum model alone, we should get better result. Now we get better result when we train it in a hybrid mode. So the next session is going to be about that. Okay. So we actually got, I think some of you may be playing with that. Let's have a break and come back in half an hour. And we'll cover applying QML to multi-class classification during the, no, but there's an easy way of doing it. There's a softmax function which could map the results obtained from the quantum model onto multiple categorical values. So you have to split the result into multi-value outcome. Each outcome is for different class. But that's actually a challenge. So that's why I'm not solving it here. But I suggest, yeah, there's a softmax function which will convert the result into multiple class outcomes. So that's for you to explore.